All right, so I'm gonna give a couple talks. Basically, I'm not in a hurry to get through this stuff. I think we probably have plenty of weeks left of the semester. I kind of expect it'll take 2 weeks, but I'm flexible about that. So we get distracted or it takes longer than I thought. I'm not opposed to going a third week. I mean, I know there might be other things. So we'll figure it out. Okay, so what I'm gonna talk about is a project that I've been working on with Hana Kong, Huchuan Li, Yang Wang, and Hei Zhu. And the first talk is kind of going to be an algebra talk, and then the second talk will be a homotopy theory talk. So this is the more technical, kind of less motivated talk, and then next week it'll be a little bit more kind of self-evident about what we're doing and why. Okay. All right. So to begin with, I'm interested in the C-motivic atom spectral sequence, and so therefore I'm interested in the E2 page of the motivic atom spectral sequence, and that's this, cohomology of motivic steam-rod algebra. Okay, so I'm kind of taking that for granted. I'm not going to tell you too much about that. Although I will remind you what the dual motivic steam-rod algebra actually looks like. So you have, I should really have put a dot in here. You have infinitely many tau i's and infinitely many xi's as well. And then infinitely xi's. And then you have this relation, this tau I squared equals tau xi equals 1. And you also have this parameter tau that you think of as sort of like in the coefficients out in front. Okay, so that's what it looks like. And for those who are thinking by analogy with the classical situation, classically you invert tau. And so if you invert tau, then ci plus 1 is just a fancy name for tau I squared. And so that's back to just the polynomial algebra in one set of variables, which is the familiar classical story. So that's the way it kind of corresponds. Okay. All right, so then if you want to compute the cohomology of the motivic steam-rod algebra, you need to know about the coproduct. And so this is the picture that I draw to remind me what the coproduct in the dual steam-rod algebra is. You look at the formulas in the books, and you see the summation over some C, some subscript, and some power, and then tensor some other subscript. And I always have trouble remembering how that formula goes, but this picture reminds me exactly how to do it. So here's how you do it. You take an element, say like tau 4, okay? And in order to read off the reduced coproduct on tau 4, what you do is you use this V-shaped diagram, okay? And what you take, so it's C4 tensor tau 0 plus C3 squared tensor tau 1 plus C2 to the 4th tensor tau 2 plus C1 to the 8th tensor tau 3. That's exactly what the coproduct is, and so forth. For any element in here, you want to know the coproduct on this, well, you use those guys. And you just, you take tensor together and you add, work down one column and work down one diagonal, up the other diagonal, and that gives you the coproduct. Okay, so for those of us who work over that finite subalgebras of the steam-rod algebra, I wrote in there in color, I kind of showed you where A of 1 and A of 2 and A of 3 sit. A of 1 is what you get when you just restrict to these three things. And A of 2 is what you get when you restrict to 6, and A of 3 is those 10, and so forth, just to kind of help you orient. And then, of course, this figure goes, this is the vertex of the figure, and it extends infinitely horizontally, and it extends infinitely down also. Okay, now there's a reason that I put the vertex in the upper right corner rather than the upper left corner, and that's to get the coproduct correct. Because if you look at the formulas in the books, the usual way that the formulas go has these higher powers on the left and the lower powers on the right, and so then it lines up, and you don't have to flip things around in your head. And anyway, it's just a little more, it's reading from right to left, but we're mathematicians, we're good at that sort of thing. There's a reason for it here. I'm not just making it confusing. There's a reason to draw it that way. Okay, so the May E1 page is, all right, so you start with this, and then you filter by, you filter the sterile analogy, filter the Kovar complex, I guess, by, powers the augmentation ideal or something like that. There's some filtration called the May filtration, and then you end up with a spectral sequence, okay? And this picture involving the coproduct ends up translating into this picture about the May E1 page. Okay, so first of all, let me warn you that the notation that you see on here for the HIJs is not the notation that you think it is. Whatever notation that you use for the HIJs, and unfortunately different people use different notation, whatever one you have in your head, it's not this one. Okay, because this is like the first time I've ever used this notation and I'm kind of experimenting with it. These problems get too easy, right? And so you have to like add complications. It's like you change the notation and you need to force yourself. No, there's actually a logical reason for it. Let me just briefly say what that is. When you think about massive products, there's various ways you can index the sorts of elements and diagrams that you need to study massive products. And in all the different ways that I have seen to deal with the sort of massive product calculus, the best, the quote, right way to index things is what you see in Peter May's matrix massive products, okay? And that's what I'm doing here. I'm using the notation that if you take as a given that matrix massive products is indexing the massive products correctly, which, that's an assumption, but I happen to believe that, then this is the indexing on the HIJs that you lead to. Okay, roughly speaking, you want to think of these as like slices of a list. Like say, modern computer languages, index a list. If you write, list bracket 1:2, what that means is just the entry 1. And if you look at a list colon 0. List bracket 0:2, that means the entry 0 and 1 on the list, but not the element 2 on the list, right? That's the kind of the convention on indexing. And that's really what you want to think of. So this is like just the 0, this is just the 1, this is just the 2, this is just the 3, this is just the 4, and that's kind of like the H0, H1, H2, H3, H4s. So the HIs are running across the top, the VIs are running down this diagonal, and then the WIs that we sometimes talk about in the Motivic context, and will come up next week, are on this second diagonal, running down along here. Okay. Roughly speaking, square knot operations correspond to shifting one to the right, and you can kind of see that up in this picture too. If you think of square knot as like the Frobenius, and you're squaring all these elements, and you're moving one to the right. Okay.
That's only rough in its treatment of the towels.
Yeah,
Correct. Otherwise,
it's correct, right? Exactly. So the way it's rough, right? So the tau 0, when you square that, you get tau T1. But that's actually correct. Square knot of H0 is tau H1. So it's
really correct.
So it is sort of correct, but you have to kind of understand what that means. It's a little bit different at the bottom. And then roughly speaking, not roughly, but the May filtration is then kind of corresponding to going down in the picture. Okay, so things that are lower down are in higher May filtration. Okay. So now,
not the May. It's true in the May. It's true in the what the May. It's true in the abutment spectrum. Not true in the May.
what's not true?
The fact that square knot.
Oh, yeah.
It's 0 in the May 1.
Oh, those
In the May abutment.
Yeah. I don't. Yeah,
the squaring operations in the May E, the initial term of the May spectral sequence have nothing to do with one thing.
It's all 0. It's just 0.
Well, they're not all zero.
So on all these. They're not 0 and 1.
Yeah. They're minor. They have a minor bit of use, but they don't have anything to care about.
Sure. Yeah. The point is, it's square one and it's square knot in the abutment.
Right.
Yeah, that's exactly what I had in mind, and even I only meant it sort of loosely. I don't mean it like any literal sense. I just mean like if you're, let me say it this way. This picture, this is how I navigate the stable homotopy groups of spheres. Is like this is the picture. These are the coordinates. Like I think how deep am I going? How far out am I going? Whatever. Like these are the coordinates, and square knot is corresponding to moving to the left in the picture. Okay.
Even though it moves to the right in the spectrum. This is.
Yeah, yeah, yeah.
Yeah.
That's right, that's right.
Right, and this is, the ridiculousness of putting, you said moves to the right of the F, and I'm putting H naught on the right, and then H one, I mean, it's all backwards around, but this, anyway, there's sort of a reason for it. Okay, so now, Andrew, before the talk, Andrew saw this, universal maxi product, and then he asked me, can you make that precise? So I think you can make it precise. So if you take, this E1 page together with its differential, okay, that's a DGA. Okay, it's a commutative DGA because the A, okay, and if a map of DGAs from this DGA into another, and I better make it commutative DGA because that's, which is annoying and I don't really want it, but that's just what it is. So a map from this commutative DGA into another commutative DGA is the same as choosing an infinite list of elements. That's, images of these guys, together with a choice of no homotopy killing all the pairwise products, together with a choice of no homotopy killing all of the threefold Massey products, together with a choice of no homotopy killing all the fourfold Massey products, and so on and so forth. Right? Okay. So it's like an infinite Massey product, where you have an infinite sequence, and all of the finite subsequences are all sort of zero contains. All those Massey products all contain zero. So, I mean, was that saying
Was
that?
it the universal ones should be, correct?
Well, I mean, yeah, I mean, I don't know, but, and then the E2 page, the E2 page is the homology of this thing, which ought to be universal in some sense, or these are the invariants of something, right? So I don't, anyway, this is just a slogan. I'm just kind of giving background on all this. I don't think, we're not going to use this universal Massey product property. I'm just kind of helping people kind of, get their bearings, get a feel for all of this. Okay, so now I'm going to adopt a particular perspective today. And this isn't the only perspective that you could adopt, but it's the one that we're going to talk about. And there's, as I said, there's a reason for it, and I'll show you a little bit about it. Okay, so I'm going to talk about the Chow degree of elements. So this Motivic Adams E2 page is tri-graded. There's the stem and there's the filtration, but there's also this extra grading, this Motivic weight. Okay, and I'm going to so you've got 3 gradings, but really you've got more than that because you can take linear combinations of those 3 gradings and get additional gradings, which, in some sense, it's no new information. And it's no new information, but it can lead to a useful perspective. Okay, so what I want to do is I want to take to take the stem plus the Adams filtration, okay, which is also known as, like, sometimes they call it the internal degree, or the I would call it the algebraic degree. It's the thing that would come up if you think about Ext groups purely in the context of algebra. It's kind of like the degree that you would use. Okay, and then subtract twice the Motivic weight. Okay, so that's sort of a random arbitrary thing to do. At least, so far. And also I should explain where this term Chow comes from. This Chow comes from the fact that this sort of like, stem minus twice the weight, that's the natural degree that comes up when people study Chow groups. I mean that, like, in the sense of modern algebraic geometry. If you're a Motivic homotopy theorist, you use the weight, but if you kind of come, like blocks, higher Chow groups are indexed on something like stem minus twice the weight. Okay, so that's kind of the motivation for it. I'm not drawing any strong connection between higher Chow groups and these things. It's just, you got to give some adjective to this degree, and so that's the one that we picked. Okay. All right, so you can do that. And then you should look at these generators of the May E1 page to see where they sit in terms of Chow degree. And what happens is that the HI zeros, the guys right along on the edge, right along the diagonals, they all have Chow degree 1. Works out. I mean, you got to look at the formulas and figure out you see Chow degree 1. But all the rest of these guys have Chow degree 0. Okay, that's just what happens. Okay, and so there's a couple things about this. A couple of conclusions that you can draw from this. But let's see here. What do I want? Let's go like this. Okay. So first of all, you could study the subalgebra of the Motivic steamroid algebra in Chow degree 0. Okay, just restricted Chow degree 0 and just call that V star. Okay, just because it's some letter other than A. I'm not saying that's a great name for it, but it's something. Okay, and what's that? That's just polynomial in the it's polynomial in this C1, C2 up through. So you get rid of the taus. The taus all have Chow degree 1. The x's all have Chow degree 0, and there's also no tau in here. Okay, it's just F2 because tau has Chow degree 2. Okay, so tau also is in higher Chow. So you just have this relatively little thing there. Okay, and then you can and then look, you look at this half algebra or dual half algebra or whatever, and you see that that's just a copy of, that's just isomorphic to the classical steamroid algebra, except all the degrees have been shifted because now this first generator is C1, which is really like the square of the original generator, and this second generator is really like the square of the original second generator and so forth. So the degrees are shifted, but it's just the usual classical copy of the usual classical steamroid algebra. And so that tells you what its cohomology is. If you take X groups over this half algebra, they're just the classical X group, but there's this degree shift. Okay, and the degree shift is that an element in degree SF, and I mean stem filtration, so like XY coordinates on the Adams chart, right? In degree SF, that corresponds to S plus 2F comma F, and then the S plus F is exactly what you need in order to make the Chow degree 0. Okay, so you think of that weight as sort of like derived from this thing, and that's of course exactly the same shift as what square not does. Right? Square not takes an element in SF and it outputs an element in S plus. Oops, that's a mistake. I mean 2S plus F. So, thank you for looking puzzled, Bob. That tipped me off that something was wrong. Okay, that's what I meant. Okay. So if you're used to thinking about square not and the Adams E2 page, then you'll have a good feeling for how this works. Okay, so I want to talk a little bit more about this because we're going to be kind of flipping back between these two perspectives. So what happens with this? What happens under the shift? Well, classically, what do you have? You have the H naught tower in the 0 step. Okay, and when you shift degrees, what you get is an H1 tower, an infinite H1 tower, which if you've explored the Motivic Adams E2 page, you're familiar with. Okay, and then you have a couple of from the origin, you have a couple of H1 multiplications, and those H1 multiplications get shifted into H2 multiplications, and so on and so forth. So everything in the classical picture just kind of gets, it's a shear transformation. It's exactly what it is. That's the right word for it. It's a shear transformation of the classical picture into this kind of like this shifted over. Okay, so that's what happens in Chow degree 0. Okay, and so that's completely understood. Okay, and what I mean by completely understood, it's completely understood in terms of classical terms, but it's if classical X is understood to say 256 steps, which is roughly speaking the cutting edge for computer data, then this cohomology of B is then understood at least to 512 steps. It's a little complicated because this thing doesn't really preserve steps, but it kind of roughly doubles things. So the point is that we have a tremendous amount of information about this Chow degree 0, okay, kind of part of the cohomology of the steam.
Does this X participate in something with geometric meaning?
Well, that's a good question, and that's kind of what a big part of what I'm going to talk about next week is ask, well, okay, fine. So you have this algebraic information, but what does that say about homotopy? Right? Like which of these elements survive, which of these elements support differentials.
The rest of
Is it going to interact with
X.
Can the Adams differentials? Right. The Adams differentials will mix Chow degree, and so how is that all going to fit together?
Does this capture the Adams integral? So in some sense, that quotient could just have differentials coming. That is, the differentials, the rest of it only enter it.
Differentials from the rest of it. So okay, let me say a couple of other things here. Let me actually go back to this. First of all, from these formulas, what you see is that everything is in positive or is in non-negative Chow degree. There's nothing in negative Chow degree. Everything is, and that's kind of what makes it so useful. You've got this tri-graded object, but what you've got is a vanishing plane. You've got a plane and everything is sitting on one side of that plane. That's structure that you should probably take advantage of. That's the point. Okay, so then so jumping ahead to next week, the Adams differentials, dr increases Chow degree by r minus 1. So the d2 increases Chow degree. That means that Chow degree 0 elements can support differentials into higher Chow degree, but they cannot be hit by differentials. That's going to be really important. That's how we'll detect that things are non-zero, basically. Once we know they don't support any differentials, then they can't be hit by anything, and they have to be non-zero. So that's the idea. Chow degree 1 elements can only be hit by Adams D2s, but they can support lots of long differentials. So, okay, all right. So Chow degree 0, we've got that under control in some sense, and then and that might lead you to ask, not necessarily, again, it's not a totally obvious, just like studying Chow degree at all is not totally obvious. It's not totally obvious, but from one perspective, the next step then is to study what happens in Chow degree 1. Okay? I mean, you could do that, right? I mean, obviously, you're not going to be able to go do that forever, but at least you might take a look at it. Okay, and we only took this next step very recently, just in the last few months. I've understood this Chow degree 0 stuff for years and years, for 10 years or more. But it sort of never really took this seriously because you have to have a reason to kind of tackle a problem like that. You're not just stumbling around trying stuff out. Well, I mean, you do that too, right? But but this is not something I tried to do because I didn't have a reason previously. Okay, so let me now give you a couple of reasons why, what makes the Chow degree 1 elements interesting. I'm gonna describe some part of Chow degree 1 that makes it seem a little bit natural. Okay, so first of all, there is a conjecture of Hugh Tai. This really kind of came out of Hugh Tai's thesis. So Hugh Tai graduated in 2020. So in the late teens, Hugh and I were thinking about some of this stuff. And here's an idea that we weren't able to solve, that Hugh and I weren't able to solve. Okay, so you can take the element E naught G to the K. Okay, in the cohomology of A of 2. Okay, that's a totally standard element in the Adams E2 page for TMF, totally kind of like natural, obviously, and I mean it in a semotypic sense, not in a classical sense. Okay, so that element E naught G to the K is in the image of the map from the Adams spectral states for the sphere. Only sometimes, if and only if K is 1 less than a power of 2. So and these types of formulas always confuse me. I'd much rather see this sequence and then I kind of know what elements I'm talking about, and then if I need that formula, I guess I can. So E naught G, E naught G cubed, E naught G to the 7. Those elements are in the image of the E2 page for the sphere. But E naught G squared, E naught G to the 4th, E naught G to the 5th, they're not in. That's the conjecture. The conjecture is that they're not in the image. Okay, so why would you care about this? Well, I mean, this is touching on things like the Hurevich image, the Motivic Hurevich image. It's not exactly that because these aren't permanent cycles, but it's clearly related to questions about the Motivic Hurevich image in TMF. So it's or in MMF, I should say. Okay. All right. So a couple of points here. So first of all, these elements, these E naught G to the K, they are in Chow degree 1. Okay, so if you can wrap your head, you can do enough computation about Chow degree 1, you can settle the fate of these guys. Okay, and that's exactly what we did. So this conjecture is now proved.
Is that all K or just the 2 to the minus 1s?
All K. This is true for all K. Yeah, G has Chow degree 0, so you get it. Doesn't change. 20 plus 4 minus 12 times 2. So. So, and this has now been proved, okay? And the rest of the talk, I'm gonna tell you more about how it gets proved, okay? Just as a reminder, I talk about these things a lot to various people in this room, but maybe not to everyone. So this element G, and by G, I mean this particular, this is the representative in the this guy in the May spectral sequence, you would call this H21. Okay, so it's the usual G, but, I mean, like this guy, it does not survive in C Motivic Ext, okay? It survives classically, and it doesn't survive in C Motivic Ext because it supports a May differential, but that May differential hits a tau torsion element, and so tau times this does survive in C Motivic Ext, okay? On the other hand, that May differential that hits tau torsion doesn't occur in A of 2. And so in A of 2, you really do have G. Okay, and so what I'm trying to say is under this map, you have an element G over here on the right, and G is not in the image of this map. So that's kind of, and it's that fact that allows these sort of questions, these interesting questions these types of interesting questions to arise. On the other hand, if you put in just one multiple of tau E naught to the G to the K, that's already in the image for all. Okay, it's just this little tiny little, one little weight just without tau. So this is one little question that remains. Okay, so that's I mean, questions were asked, now questions are answered. That's so this method that I'm talking about today, or I'm going to talk about, is useful for something. I guess that was the point. Okay. And then the other thing that there's sort of another thing about these E naught G to the Ks. Okay, so many years ago, Berkey, you and I computed the H1 periodic simulative T2 atom T2 page. So I just literally mean you take this Motivic Ext and you have an element H1 and you just invert it in the sense of naive ring theory, right? You just invert that element and we completely work and we got this very nice clean answer. Okay. But see, there's and that's fine, that's a nice answer. But if you really want to, the motivation behind a result like this for me is that this H1 periodic computation is an approximation to the computation that I really care about. And there's a localization map here which detects some things, right? Some elements map non-zero here. There's a big kernel, you want to sort of understand this localization map. If you're going to make any use of this computation, you really have to know the localization map. Okay, and we computed the localization map in range, but we weren't able to compute the entire localization map. We have these nice sort of VNs over here, but we didn't actually know what the pre-images were. Okay, and I mean V1 to the 4th is a little different. I mean, it sort of corresponds to V1 to the 4th, I guess. V2 corresponds to C naught. V3 corresponds to E naught, and we could do some of these. I think we could do these this much just by kind of, because it's in the known range. We could kind of inspect Adams charts and just kind of see what happened there. But this one, we didn't actually know what that V6 was, the localization of E naught G to the 7th. Okay, and that's something that comes out of this work also, is that we now do know what that these guys that now we know survive are in fact mapping to the VNs. And so it's really kind of finishing up an important piece of this H1 periodic story that was a loose end for many years. Again,
there's an obvious pattern. Oh, yes, you have it. So the one on the right is the generic.
Yeah, right, exactly. But again, like I look at formulas like this and I just get confused what they really mean. And then when I see this pattern, it all of a sudden makes more sense to me. That's my idiosyncratic perspective. So, all of this has this feeling of kind of like a really clean answers to, and not, clean by the sense of like really not that much effort. I mean, when I get into the methods, it's like, it's not that hard. Turns out like that our approach wasn't that hard to do. So clean answers to really hard questions that nobody was asking. That's kind of what all of this is, I mean, I know there's the Q ties conjecture, but and this localization thing, but and these are nice, these are loose ends, but it's not like we really need to know them. It's not like we're, translating them into results about homotopy theory. And so anyway, it's kind of a funny thing, but that's where we're at. Okay, so that's one. So this E naught G to the K elements, that's one reason that I wanted to study Chow degree 1, Chow degree 1. And then there's another reason, and this was actually the main reason that we wanted to study. Okay, there's a particular product, a particular element here, H naught H2, we know what those are, times, and then H2G to the K. H2G to the K is actually an indecomposable in the Motivic Ext. Remember, G is not an element, but H2G to the K is, and so that's 3 indecomposables there. So that product turns out to be non-zero in Motivic Ext. Okay, for all K greater than or equal to 1, not for K equals 0, that's H naught H2 squared, that one's 0. But once you get K greater than or equal to 1, all of those products turn out to be non-zero. Okay, so we wanted to know that. And so why do we want, oh, as I said here, right, H2G to the K is a non-zero decomposable, and its Chow degree is 0. The Chow degree of this product is 1. Okay, so again, you could potentially detect this in Chow degree 1. And the reason that we wanted to know that these elements were non-zero was that they, and this we'll talk about next week, but they lead to an infinite, a G-periodic family of exotic atom differentials. And by exotic, I mean not seen classically, just if elements that are tau torsion, and so they have nothing to do with the classical picture. Okay, so that's the real, that was really kind of how we got on this. Like, it was sort of clear that there was this G-periodic family of differentials, but how are we going to actually prove that there's a G-periodic family of differentials? Well, we need to know that the targets are all non-zero, and so then, and then they're in Chow degree 0, Chow degree 1, and so we then took a closer look at Chow degree 1, and we worked it out. We established they are all non-zero. Okay, so that's the other motivation, and then some of this will, again, this slide in particular will come back to next week. And one thing I'll say this, you look at these elements, H naught, H2, G to the K, and you think, oh, well, can't you use the cohomology of A of 2? It looks like the kind of thing that the cohomology of A of 2 would be good at detecting. But it's not, it's 0 in the cohomology of A of 2. You have to do something. It's not, it's not 0. This product is 0 in the cohomology of A of 2. So that's the obvious thing. Like, if you just wrote this on a slip of paper and you hand it to me and say, quick speed test, prove it's non-zero, the first thing I do is like say, well, let's look at the cohomology of A of 2. It looks like an A of 2 kind of thing, but it turns out not to work. And that's just getting at the subtlety of all of these questions. Okay. All right. So how are we going to do this? So now we're ready to start talking about the method. Okay. So the first thing is that what we want to do. So we're just going to try to focus on Chow degree 1. And so I'm just going to pull out the part of the cobar complex that's in Chow degree 1. Okay, so the tau i's all have Chow degree 1, and the Xi's all have Chow degree 0. So what I'm saying here is you can take anything you want involving the Xi's, but then you combine it with exactly 1 tau 0, or with exactly 1 tau 1, or with exactly 1 tau 2, and so forth. Okay, and that'll give you the thing, kind of like the part of the cobar complex that's in Chow degree 1.
And square brackets doesn't mean polynomial generator.
No, it means like cobar. It's like the cobar notation. And I'm calling it a differential graded object because it's not an algebra. It's a module over the cobar complex for B, I guess. That's but it's got a differential on it, and that satisfies a Leibniz rule in an appropriate module sense. All right. So then you filter by. So you want to take the homology of this thing. Okay. So you're going to write down a spectral sequence. So we got to filter it. So we're going to filter it by summance. Okay. So what I mean a little more precisely is that this is the smallest piece of the filtration. Okay. And then this is the second piece of the filtration. And note that the coproduct on tau 1 involves a tau 0. So this what I've drawn here is still closed. It's a differential graded subobject. That's what I mean to say, right? It's still closed on the differential. And then the next piece involves these 3 terms. And because the coproduct on tau 2 involves involves tau 0 and tau 1, so it's closed under the coproduct and so forth. Okay, so I'm taking differential graded subobjects just by kind of adding one summand at a time. Okay, and then that leads to a spectral sequence in the usual way. If you have a differential graded anything and you filter it any way you want, then you get a spectral sequence. Whether it has good properties and you compute it is a different story, but you get a spectral sequence. Okay, and then so this is E0, and then E1 is when you just kind of take the part of the differentials that don't shift the filtration at all, which really is just kind of like the differentials that are internal to this cobar for B star. Okay, so when you take the differentials internal to cobar B star, that you get Ext of B. Okay, and so E1, this cobar becomes Ext, and then I'm going to write this bracket tau 0. I'm going to write it as a V0 because I don't know. I don't have to do that, but I just felt like doing it. It's kind of suggestive of something, or I don't know. Okay. And then similarly here, this cobar, this one, the internal differentials give you XB, and then this bracket tau 1 is V1, and so on and so forth. Okay. So you have infinitely many copies of this, a direct sum of infinitely many copies of this XB. And let me remind you that this XB is not something mysterious at all. It's something very well studied and well understood. It's just classical X, but this isomorphism has a degree shift. So you got to be careful when you do that. Really in XB, you've got like the infinite H1 tower. When I write it this way, that infinite H1 tower looks like an infinite H0 tower. So you got to be careful about whether your degrees are doubled or undoubled at kind of any given moment.
Which do you mean? You don't really mean X classical, you mean square root of X classical.
No, I really mean it's isomorphic to that, right?
You're taking your cat, you're doing unshearing.
Yes, I'm unshearing it.
Okay.
Exactly. Yeah. So what happens, as you know, is that there are elements in classical X whose square naught is 0. Okay? But motivically, that doesn't happen. They're all non-zero. They're just some of them are tau torsion. Okay, so that's roughly speaking so that's why I mean it's literally. Okay. All right. So it's just you get a bunch of copies of X, and this is in terms of the filtration of the spectral sequence, this is like filtration 0, this is filtration 1, this is filtration 2, and so forth. So the differentials in the spectral sequence are going to shift between these copies. Okay, and then you can go look up the formulas for the coproduct, and you can just find out that these are the differentials. Okay, so this D1 on V0, so that's in the low, that would go to filtration -1, there's nothing there, so that one's got to be 0. Then if you take V1, the generator here, it should go to something in here, and the thing it goes to is H1 times V0, and then V2, that should go to something in here, and the thing it goes to is H2 times V1, and so forth, all the way down in general. That's what turns out to happen. Okay, so now I'm going to regrade from here on. I'm going to regrade everything with these classical undoubled degrees. So in other words, rather than using the top line there, I'm really going to use this second line. Okay. So when we draw charts, we're going to see some vertically infinite towers. And those look like H0 towers, but because of we've undoubled it, they're really representing H1 towers in C-motivic Ext. Okay, so sorry about that, but this is what it takes to get this. You got to be flexible about this. We found that it was necessary to be flexible about this grading issue in order to carry out the computation. Okay, so I'm going to regrade with these classical undoubled things, and then this H1 in XB is really H0 in classical X. And this H2 in XB is really H1 and so forth. Okay, so the E1 page looks like what I've drawn there in the middle. Okay, that's the V0 copy, that's the V1 copy, that's the V2 copy, and so forth. And the D1 shifts by 1 and multiplies by H0, multiplies by H1, multiplies by H2, and so forth. So when we stumbled across this is sort of like it's sort of a weird thing. It's almost like a joke, right? Like here's a stupid thing you could write down. Like that's a chain complex, right? You apply the boundary twice and you get 0. Well, yeah, I guess that's right. Hi times Hi -1 is 0. So you could do that, but you know, you never, it's like,
It's the most natural thing in the world to do, though,
but
if you had thought to do.
yeah, but it doesn't really mean anything, right? You could write it down, but like, you wouldn't expect it to mean anything, right? Unless you know, so this is already pretty remarkable. We got to this point, and I already was struck, like, this is like a surprisingly kind of elegant, like, natural thing to look at, okay? So then, fine, all right, so then you compute E2, and that's easy, right? So you've got the co-kernel of H naught here, and then here you've got the kernel of H naught modulo the image of H1, and, you know, and so on and so forth, okay? And then you get to this, so then you have to worry about the higher differentials, okay? And so now, folks, now it gets even more interesting and more like just more elegant, okay? So let's take a look at look at the D2s are supposed to kind of skip over too. You know, this is sort of a weird way of drawing a spectral sequence. This is again like filtration 0, filtration 1, filtration 2. I mean, you might want to stack them up or something, but I really want to keep my pictures are always stem and Adams filtration, and this is some, this other filtration that I don't really want to plot. Okay, so let's just look at this D2 here. This one at the bottom might feel a little exceptional because it's co-kernel of H0, but it's not really exceptional. It's just the notation was a little different. So let's just look for a formula there. So we're looking for some formula that goes from the kernel of H2 module the image of H3 into the kernel of H naught module the image of H1. Okay, well, if you've sort of, you've studied the kinds of mathematical problems that I've been studying for many years now, you need to define, let me just say this way. Define an interesting function from the kernel of H2 module the image of H3 to the kernel of H not module the image of H1. Just write down a function. Well, this is a zero function, right? But write down an interesting function. If you ask me to do that, this is, I mean, to me, it immediately jumps out at me. Like we know what kinds of tools there are that are only defined on kernels and are only defined up to images of multiplication. We know that sort of thing. That looks a lot like a Massey product, okay? And so that's exactly what happens. The natural function that's defined from the kernel of H2 module image of H3 to the kernel of H naught module the image of H1 is the function that takes x to the bracket H1, H2, x, okay? But I mean this, of course, I mean it in this quotient sense. So when you ask me about indeterminacy, I say, no, these are well-defined functions now because I've modded them out. Okay, so there's actually 4 restrictions here, right? I've restricted to a kernel and I'm modding out by an image. And so there's 4 things. Look what happens here. Restricting the kernel of H2, that makes this like, well, non-empty, or like this makes this bracket well-defined. You have to have H2x is 0, otherwise you can't form that Massey product. Okay, so the kernel of H2 is relevant for that reason. The image of H3, what is the modding up by the image of H3? That's saying that the function should take H3 multiples to 0. So if you apply this bracket to an H3 multiple, well, what you get, you can pull out, there's a kind of a standard Massey product relation that you can pull out the y, and then you've got H1, H2, H3, comma y times y, and H1, H2, H3 is kind of like 0 on the nose, like it's a sort of, anyway, it's 0, okay? So this, this mod image of H3 is really kind of knowing that this Massey product is 0, just kind of a very kind of, clean explanation. Why is it taking values in the kernel of H naught? Because if you take any value of this function and you multiply by H naught and you apply a standard shuffle, then you get H naught, H1, H2, which is also 0. Okay, so this complex also knows about that about the shuffles, and then that thing is 0. And then finally, modding out by H1, that kills the indeterminacy and makes it kind of a single valued function.
Well, it kills off half the indeterminacy.
Right, good point. Okay, so what happens though is that, see, x is a variable, and so you can't kind of predict, predict the degree of this, but H1 and H2 are fixed. And so there's kind of a fixed degree where the cycles would need to live, you need, it's x times, 5 comma 1, I think, 5 comma 1. And there's nothing there in x. For any x, well, because it's just 5 comma 1. It's always 5 comma 1 times x. And so it's always 0.
So the other half is automatically 0.
Automatically. Yeah, exactly. And for all the rest, obviously, I'm writing it this specific one, but of course.
But this is the sort of second layer in the universal Massey product.
Yeah. Yep, exactly, right? And then, of course, more generally, you know, I did it just one case, but of course, that's what's happening all along. And then you get to the high, so that's the D2s that are in terms of threefold massey products. And then you can get to the higher ones. Okay, and then the D3 is in terms of fourfold massey products and so on and so forth. Okay, and there's a really remarkable thing that I didn't write a slide because wasn't going to take the time during the talk to do this, but it was a great exercise to work out. You know, this is defined on the E3 page, and so there are certain conditions that have to be satisfied, and it takes values and some sort of complicated other thing. And those conditions to land and to be well defined on the E3 page are exactly ruling out the indeterminacy, making it well defined, kind of cleaning it all up, right? So the theory of fourfold massey products is actually kind of messy. In general, there are some aspects of like the algebra of massey products that aren't known, like the indeterminacy of an arbitrary fourfold massey product. It's not even linear. It's not even necessarily linear subspace. So how do you handle that? Like, we don't really know how to do that. But modding out by the images of the previous differentials in this situation kind of wipes that all out and makes everything super clean. It's almost like this is the structure that, that massey products were an attempt to approximate. I don't know exactly what I mean, but it's just, everything just fits together in just the right place, and it all kind of comes together. Let me just mention, I'm just going to, this is sort of an offhand comment, but Christensen and Franklin have an article in which, it's roughly speaking says, I mean, the theorem is roughly speaking, the Adams differentials are total brackets. Okay, in an appropriate sense, you have to interpret that in an appropriate sense, but roughly speaking,
That's actually pretty obvious.
yeah, fine, okay, but still, fine, I don't disagree with that. It's kind of so general and kind of, and the generality with which they prove that kind of shows that it has to be, it works so generally, well, it has to be diagram chasing, because what else would work? But, that's what we're seeing here. We're really kind of seeing a concrete instance of this kind of general phenomenon.
And it really always is just the massey product of longer composition.
Yeah.
And the tower.
Right. Exactly, and then those are the D1s. That we calculated earlier. Okay, so here's a problem. It's being worked on right now. Compute the Chow degree 1 spectral sequence by machine to the 512 step. And I say 512 because we have classical 256 data. So, but then when we shear it, we're going to get out to 512. Okay, and this can all be, the E2 page can definitely be done. I mean, it's just a question of looking up the information. We have the product table up to 256. We just got to look up, we've got to find the kernel of H naught, module the image of H1. That's just tabulating data that we've already computed, basically. But I think you can actually compute the higher differentials as well by machine. Okay, so here's how I think this ought to go. And this is a little speculative, but first of all, if you want to compute products HI times X in X, classical X, there's kind of a standard way that you do it. You've got to lift chain maps and just do what you got to do that the homological algebra textbook tells you to do. But there's actually a shortcut that makes these particular products vary. They're not arbitrary products, not X times Y, it's just the HIs, specifically HIs times something, okay? There's a very effective way of doing it. And roughly speaking, what you do is you look at the minimal resolution and you just read off certain terms in that minimal resolution. And that check is for the dual, because that X is in X. And so that X dual is the thing in the minimal resolution that dualizes 2X. Okay. But anyway, you just have to read off certain, you can look at, if you have the boundary maps of the minimal resolution, you just can read off certain terms, square 2 to the I, and you'll get terms with certain coefficients, and you get a kind of a really quick way of computing HI times X. Okay. So I don't know this for a fact, but my feeling is that the higher differentials, that those massey products like H1 comma or H1 comma H2 comma X, those types of matching products involving strings of HIs and then a single X on the end, those ought to be effectively computable just by looking, not looking for square 2 to the I coefficients, but looking at these PIJ, like these Milnor basis elements in the minimum resolution. I don't know that, but the degrees line up and it feels kind of right that that's the case. But and again, I mean it only in this sense with those quotients, throwing out all the indeterminacy and only making it, making it all well defined and all that. I don't mean the full massing product with all of its indeterminacy. I just mean that what I really mean is the differentials in the spectrum sequence. That's what I mean. I feel like differentials ought to be able to be read off of this, although I haven't proved that, but that's the feeling.
The note, the real only thing you really need about the HIs is they're in homological degree 1.
Right.
And
Yeah.
therefore they're dual to some generator.
Yeah. Yeah. And, and these guys are sort of, they're in homological degree 1. I mean, the HIJs, they don't survive, but
Right.
they're still in homological degree 1. They just don't survive. So I don't know. But it feels that way. But we just kind of do a diagram chase that hopefully that comes out. And then you could completely compute the spectral sequence in a huge range. 512 steps is like enormous. Okay. All right, so let me show you a kind of a schematic of, this is like a qualitative version of the spectral sequence. Okay, so the idea is that there was this, V naught copy, and it was, its E1 page was V naught times classical X. And so that's what the black represents. The black represents the embedded H naught tower in classical X together with the vanishing line of slope 1/2. And I've actually drawn this to scale where the y-intercept of this line is actually correct. That's literally the vanishing line of slope 1/2. Okay, and then the second, and that was like filtration 0 of the E1 page. Filtration 1 of the E1 page is V1, and then there's again another copy of classical X shown in red. And then the second stage of the filtration is another copy of classical X shown in blue, and then green, and then purple, and then the last one, that orange one, out on the end. Okay, so that's what the E1 page looks like, I guess, where it's just X groups. Okay, and then the black, you get the black for E2. The black gets replaced by the co-kernel of H naught. And the red gets replaced by the kernel of H naught mod with the image of H1 and so forth. Right? So the E2 page would be a lot more sparse. Okay.
What are the black dots circled in yellow on the red line?
So that's I'm just going to get to that. I was just explaining. So remember, there were two families of elements that we were interested in. Okay. And it turns out that these two families of elements are detected in high filtration. That's kind of what makes them accessible from this perspective. It's kind of amazing. You do all this work and you get this kind of beautiful structure. Look, I mean, look at that E1 page with the HIs in it. I mean, you'd study that, like, even if you didn't have a reason, I mean, you'd study that thing, right? But then these guys are just sort of like sitting on top. I mean, you have this, anyway, it's like this, it's not like a needle in a haystack. It's like the haystack, and you just sort of shake up the straw, and then the needle is just sitting right on top of the haystack. That's kind of what happens. So the red, the purple ones are, or pink, I guess. The pink ones are where the E naught, that E naught G to the K elements are sitting, and they're actually on the H naught towers. Sort of, and then those H naught towers are, remember, because of the doubling, those vertical arrows really represent H1 towers, and that's E naught G to the K being H1 periodic that we kind of touched on. So they're exponentially spaced out, because that's the way the degrees work. On the other hand, the yellow elements are evenly spaced, and that's this H naught H2 times H2 G to the K. So, yeah, and you can, so you have to do a little bit of, so how do you know that these, right, okay, so how do you know for example, if these things are non-zero, right? So fine, you draw this picture, but how do I know that this element isn't hit by differential? So I'll tell you how, okay? In this is, this is Adams gradient, this is stem filtration. I'm not showing you the filtration of the spectral sequence. Well, that's in color, I guess, okay? So because of that, all of the differentials all just go over one and up one, okay? So if this yellow dot were to be hit by something, that on this picture, that element would be right there. Okay, so fine, so you gotta go look what's there. But look where it's sitting. It's only the first three pieces that are relevant. The green line is already below. So there's not very much to check. You can explicitly make a list. You can explicitly write down all the elements that are there. And I forget whether there's none or whether there's something, but we know it's a permanent cycle or something like that. But it's not hard once you realize, oh, it's actually really sparse in this range. And the same thing with these guys, it's because they're H naught periodic, they can't be hit by anything because there's nothing H naught periodic that they hit. But then you have to worry about whether they support a differential. But again, like right here, look, there's even less to check. There's only two pieces to check, the black and the red. There's almost nothing to check, and you find, oh, there's nothing there. So all of these, all of these guys, they all support differentials. And then as soon as you get to the place where there's nothing to hit, well, then that's the one that survives, and then all the way up. So it's actually really easy kind of proof by inspection at this point, once you kind of see what you're looking at.
Meaning that the ones that are E naught G2 and non 2 to the n minus 1, there are possible targets.
Well, no, those guys don't really, what happens? They're not in this picture. They're like somehow, like they're not even there in the E1 fish. See, that's the thing. This spectral sequence is filtering the whole story in a way that's really incompatible with the way that we're used to thinking about this stuff. And that's kind of like, that's really kind of its power, is that it's like you've taken the thing, you turned the problem on its side, and we're seeing the whole thing from a totally different perspective. So I think that the answer to your question is that the actual, let's say like E naught G squared isn't even there in the one page somehow. And that's strange, but that's I think that's exactly what's happening. It's sort of odd.
But also is it the case that it's the knowledge of the vanishing line, say in the green part, that says it can't interact with
Yeah.
the.
Oh, yeah. Yeah, the vanishing line is
Vanishing playing a really key role.
definitely. I completely agree, right? And the failure, right, the exception to the vanishing line, right, and with the H naught towers is also playing a key role because that's this interesting family that's sitting above these vanishing lines. Just what turns out to be just what we want. Okay.
Draw Paul Schick's attention to this stuff, but
All right. So it's 3 o'clock. So I got most of the way through the presentation, but I didn't get all the way through. So do we stop here and then just kind of pick up next time and then spill over to a third week? Because if I do that, then I'll definitely want to spill over to a third week.
that would be my preference, because
Okay.
I still have some preparation.
Okay.
for work.
That would be my preference also. Okay, so let's just plan to do that. And then I'll give you guys a little bit of a reminder about where we're into the charts, kind of like, part of the talk at this point. So it'll be relatively lighter. It's not going to, there's not be a lot of formulas. Okay. All right. And then we'll plan to go. The last talk might only go half an hour. We'll just see how things go. Okay.
Best